So we've talked a lot about energy off and on up to this point. In the beginning we talked about light energy and how that electrons and their energy levels, when light energy is absorbed by those electrons, it gets converted to potential energy when the electrons get excited and move to a higher level. And then if those electrons relax back down to a lower level, then that energy is released. We talked mainly about light having energy, and we talked about kinetic energy. What's the best way to get a sense for how much kinetic energy is in a sample of a substance? Right, measure the temperature. Yeah, we talked about temperature as being the way to measure the average kinetic energy, and we saw a lot of visual representations of simulations where the faster the molecules are moving, whether it be vibrating or rotating or flying through space, the more kinetic energy they have. Keeping in mind that at a given temperature, some are moving slower, some are moving faster. So the temperature measures the average amount of motion or speed that those particles have, their kinetic energy. What's the best way to judge how much potential energy something has? Yes?
Resistance to forces.
So that's, that's a, like, potential energy for objects would have to be resistance to forces.
Not like a good way to word it, but like as far as like when it's higher, there's more potential energy because it has more force that can act on it.
Okay, right. So, right. It's not the resistance to forces so much as it is the possibility of exerting force. So, in a physical sense, if you have an object that's been lifted up in the air, it has the potential to have the force of gravity exerted upon it and tumble to the ground. Also, you could think of like a spring. If you have a spring and you stretch it, now it has the potential to snap back. Yeah, so if it's basically we look at the stability. How stable is something? And that goes for large objects like objects you might lift in the air, or springs, or planets. It also goes for molecules. So if you have something that's stable, it's low in potential energy because it doesn't have the potential to fall or snap back or undergo changes in the arrangement of the electrons. If something is unstable, then it has more potential energy because it has the potential to undergo some change in its structure or location or something like that based on its instability. So we also talked a lot about potential energy, and we said potential energy goes up when you break attractions. Because when you break attractions between particles, you're giving them instability, you're giving them the potential to reform some attractions in some way. So that's all what we've said already this semester. So we're going to apply that to some reactions and look at quantifying some of the energy changes associated with reactions. So before we do that, we need to talk about how chemists and scientists define exchanges in energy, because we're going to find out here in a little while, and we probably already have talked about this, that the universe doesn't create or destroy energy. You could take energy and convert it from one form to another, but you don't usually destroy it or create it. So what we like to do is, if we have a chemical reaction or some object that we're studying, we define that as the system. And the system might go up or down in energy. It might become more stable or less stable. It might have the particles move faster or slower, so it might change its potential energy or kinetic energy. But it's not going to create or destroy energy, so it will be exchanging in some way energy with the surroundings. So the surroundings is everything else in the universe. If you have a reaction occurring in the lab, the immediate surroundings is usually the solvent surrounding the reaction, or the container, or some temperature bath that you might have the reaction sitting in, or the room. Eventually that energy exchange with the surroundings will be dispersed throughout the universe, but we're not worried about the time frame that requires for that to happen. So we're more concerned with the exchange between the reaction or the chemicals or the substance we're dealing with and whatever's immediately surrounding that, which is usually a liquid solvent, but not always. So since we're looking at things from the reaction point of view, if the reaction absorbs energy, the reaction increases its energy, that would be a positive. And if the reaction releases energy, that's a negative. We're defining that from the reaction's point of view, right? So we're not actually increasing the quantity of energy or destroying energy with a positive or negative sign. That just means we happen to be looking at it from the reaction's point of view. Energy is going from the surroundings to the system if it's positive, or from the system to the surroundings if it's negative. So we'll see some examples that illustrate that. So in thermodynamics, we're talking about exchanges of energy. We have to be able to quantify energy, so we need a unit to do that. So when we talk about heat, that refers to thermal energy. That is both the kinetic energy for particles, which we use temperature to measure, and the potential energy for particles that we would use something called enthalpy to measure, which relates to stability. Like we said, if it's unstable, it has high potential energy, or high enthalpy is just another word for potential energy for chemicals. So then, as we said, it's going to either be absorbed or released by the system. What if you had a system that was isolated from the surroundings? What if you had a situation where the system couldn't exchange any energy with the surroundings? Well, really, that's not possible because the universe is surrounding everything. You can't take something out of the universe and just have it undergo some change in isolation. So there are ways to create insulation. So, if you think about your home in the winter, if it actually eventually it does get cold, you're going to want to have a well-insulated home, right? So you have insulation between your home and the outside. That means when you heat your house, the heat shouldn't be escaping. So that's never going to be perfect, though, right? So if you turn the heat on in your house and then you turn it off for a few hours, it starts to get cold because the heat is escaping. So there's always the ability for heat to exchange with the surrounding, but you can create, with good technology, a pretty good form of insulation, which we'll talk more about later. But there's always going to be some exchange between the system and the surroundings. And the energy that's exchanged, originally the unit for that was a calorie. So a calorie is a unit of energy. It's the amount of energy it takes to heat 1 gram of water by 1 degree Celsius. So if you have a gram of water at room temperature and you increase its energy, a gram is not very much, you increase its energy by 1 degree Celsius, which is also not very much, that takes 1 calorie of energy that the water must have absorbed. The metric unit is the joule, and a joule is about 4 times more than a calorie. So primarily we'll be using joules, but a lot of scientists still use calories, so the relationship between them is something that is something you might use at some point in the future. Just to point out, a calorie is not the same as a nutritional calorie. They're measuring the same thing, but a nutritional calorie is actually 1,000 calories. So that's confusing. I don't know why they did that. probably because when you look at a meal and you're maybe thinking about how many calories it might have, you don't want to think about it having 200,000 calories. That just numbers are not in a range that is easy for people to think about. So a calorie is a very small amount of energy. It doesn't take much energy to increase the temperature of a small gram of water by 1 degree Celsius. So your body needs a lot of those to function. So a nutritional calorie is spelled with a capital C, and that's actually 1,000 lowercase c calories. So we're talking about calories. We'll be talking about lowercase calories. So that's much smaller than a nutritional calorie, which is 1,000 times that. Okay, so here's an example. Here's an example where the system is releasing energy into the surroundings. So here I've got hydrogen and oxygen. So if I think about what those look like, they're going to come together and they're going to form 2 water molecules. So what we already said this semester was, anytime I break attractions, that could be any attraction. It could be a gravitational attraction, a magnetic attraction. It could be attraction for electrons in a nucleus. It could be a covalent bond. It could be an ionic bond. It could be a hydrogen bond or London forces. Any attractions I break requires energy to be absorbed. Right? The attraction is holding particles together. If you break an attraction, usually for the particles, that has to collide with something with enough energy. That energy has to be necessary to break whatever the attraction is. So in a chemical reaction, I always have to break attractions. So that's always a positive quantity of energy. Without any energy in the surroundings, I can't break any attraction. So a reaction like this that would normally release energy still needs some energy to get started. There's still an energy necessary to start the process off, to break these bonds. That's a positive quantity of energy. But because energy is conserved in the universe and can't be destroyed or created, then if I form bonds, then when I form new bonds, energy is released. So a chemical reaction is always a balance between how much energy had to be absorbed versus how much energy had to be released. It's very rare that the amount absorbed is going to be exactly equal to the amount released. In many reactions, the amount absorbed will be more. So I'll have a net overall increase in energy for the system from the surroundings. But in this particular example, it just so happens that the new bonds are much more stable than the old bonds. So relative to the new bonds, these are somewhat unstable. They're not really unstable. They don't have broken octets and lots of formal charge, but just compared to the products, they're a little bit unstable. So we have reactants versus products, and what we're seeing is on the product side, the electrons are just allowed to get closer to the nuclei. They're more stable because the oxygen can attract them closer and hold them tightly and form stronger attractions. So it's more stable with stronger attractions on the product side. So if I only have to put a little bit of energy to break the bonds, but then a bunch more energy is released, I have a net quantity of energy released. And so the system releases that heat into the surroundings. So that is called exothermic. Exo means out, and we're always looking at it from the point of view of the system. And so heat is coming out of the system. So if that heat is released from the system has that heat in the form of potential energy. Right? Because if these bonds are a little bit unstable and the electrons are not arranged in the most stable way as close to the nucleus as they can get, there's the potential for those bonds to be rearranged into a more stable way to stabilize the electrons more, and that has the potential to release energy. So the system is starting with potential energy, when the reaction occurs, it releases that potential energy into the surroundings, and the surroundings absorb that energy, usually expressing it in the form of kinetic energy. So most chemical reactions, if they release energy, it's because potential energy is converted to kinetic energy. And if the surroundings go up in kinetic energy, what do I expect to observe when I measure the temperature? Increase in temperature, right? That's why when I burn something, the temperature goes up. Because burning is a release of potential energy that was present in the fuel, and when the electrons are rearranged and made more stable, that energy is released in the form of heat into the surrounding. So exothermic gives a temperature increase. The opposite would be endothermic. So here I have a situation where, in this case, I've got mercury and oxygen, and I'm going to do an oxidation reaction to make neutral mercury and neutral oxygen. So I have to take 2 electrons from this oxygen and transfer them to the mercury to balance its charge. So what's happening here is I've got an O2 minus and an Hg2 plus. This is a redox reaction. The oxygen is losing electrons. They're going over to the mercury. So when I break the attraction initially, I have to put energy in. I have to put some energy in to overcome the attraction that those electrons have to the oxygen. And I have to then, when the electrons get to form a new attraction with the mercury, when the electrons come over here and get next to the mercury, that releases energy. So again, it's always some energy absorbed, some energy released. Then I have to compare the 2 quantities. And in this specific example, I find because the oxygen has a higher electron affinity, it attracts the electrons better than the mercury does. So if I take the electrons away from an area where they're stable and they're forming strong attractions, that requires a large quantity of energy to overcome that attraction. And then if I only form a weaker attraction, it's not going to be as stable. And so in this case, the amount of energy released is going to be small compared to a larger amount of energy absorbed. So I have a net energy that must be absorbed by the system. So we call that type of reaction, and there are many examples of that, endothermic, because endo means in, and the system is taking energy in from the surrounding. So in that case, the energy is taken in. The energy is necessary to break attraction. So the kinetic energy in the surroundings, kinetic energy in the surroundings, some of that is decreasing and some of it is going into the system and becoming potential energy as I have weaker attractions now and more potential for the electrons to rearrange in some way because they're not held in a stable way close to the mercury's nucleus. So in that case, I see the kinetic energy decrease, and so the temperature decreases, right? Because temperature is a measure of kinetic energy. Any questions about that? Yes?
Why is the endothermic represented with a positive delta H and the exo as a negative delta H?
Because we're looking at it from the system's point of view. So there's no net change in energy. The energy is just transferred either from the system to the surroundings or the surroundings to the system. But if what we're interested in is the reaction itself, what we want to know from the point of view of the reaction is its energy going up or is its energy going down. So if the system's energy is going up because it's absorbing energy from the surroundings, if the transfer is going from surroundings to system, then that's positive because we're looking at it from the system's point of view, it's increasing its energy. If it's the opposite and the system is transferring energy from itself to the surroundings, then just looking at it from the point of view of the system, it would be negative because it's losing energy. Other questions? All right, let's take a look at this video here.
Consider the diagram where the universe is represented as the system and surroundings. The system is the specific part of the universe that is of interest to us. In this case, the system is the block of ice. The rest of the universe, outside the block of ice, is called the surroundings. In this animation, both macroscopic and microscopic views of ice are shown. Let's show a transfer of heat from the surroundings to the system. At 0 degrees Celsius and a pressure of 1 atmosphere, ice melts to form liquid water. To melt a solid, attractive forces around the particles must be overcome. As heat is absorbed by the solid, particles begin to move about more vigorously, and some particles break free from the attractions of neighboring particles.
What's the change that's occurring? Right.
Measurements show that for every mole of ice converted to liquid water at 0 degrees Celsius and a pressure of 1 atmosphere, 6.01 kilojoules of energy is absorbed by the system, the ice, from the surroundings. When heat has to be supplied to the system by the surroundings, the process is called an endothermic process. Click on the button below to look at the reverse process, the freezing of water.
Know that there will be a quantity of energy that has to be absorbed. Anytime I break a bond, it's less stable, right? When the water melts, the water molecules have more motion, so they're not able to line up and form a maximum number of hydrogen bonds with all the neighbors like we saw in the picture in the beginning. So that energy has to be absorbed. It's absorbed because it's needed to break attraction. And we can quantify that. We can see exactly how much energy is needed to absorb it. What if I were to melt a large chunk of ice versus a small one? Would it require different quantities of energy? So if you go to the beach and you pack a cooler full of ice, does it take longer for the ice to melt if you have more ice or less ice? Yeah, if that cooler is not perfect seal and heat gets through the cooler and it melts some of the ice, if you only have a little bit of ice in there, it's going to melt fast because it doesn't take much energy to melt it. If you have a huge amount of ice, it's going to last a lot longer because it takes a lot more energy before it's melted. So if you have more bonds to break, it will take more energy to break them. Each individual bond requires a certain amount of energy to break, whether it's a hydrogen bond or a chemical covalent bond. So if we want to report a specific quantity of heat necessary to break water, we can't just say, oh, it takes 10 kilojoules or 6.01 kilojoules to break up the hydrogen bonds in water and make it melt, because it's not. It depends on how much water you have. So energies for reaction are extensive properties. They depend on how much of the sample you have. If you have more, it takes more energy. If you have less, it takes less energy. So when we report these, we say how much energy per mole. If I had a mole of ice to melt, then that's how much energy it would take. How much energy would it be if I had to melt 2 moles of ice? Well, it would be 12.02, right? It would be double. And so it's proportional that way. If I have double the number of bonds to break, it's going to take twice as much energy to break them. Right, so that was a nice demonstration. Just hopefully that will help you remember that to break bonds, energy must be absorbed. That's always endothermic. When you form bonds, it's always exothermic. If you're doing both, like the 2 reactions we saw here, if you're both breaking bonds and forming bonds in a reaction like this, then whether it's exothermic or endothermic depends on how stable the old bonds were versus how stable the new bonds are.